Thank you, Jacob. I don't know if it was your intention to have this kind of mini reunion of folks so dear to me, by which we have a collision with our present era, with an era so far in the past, but I appreciate it nonetheless, whether it was your intention or not. I'd like to say a little bit before I get started on the content of my talk about some of the background for it. The talk that I'm giving is based on a paper that I have drafted in and I'm revising. And in the paper, I'm focusing on a range of examples involving infinite idealizations that are not just focused on physics. I have some examples from mathematical ecology, for instance. And in addition, because the paper is aimed for an audience primarily in philosophy of science, I do a lot more work in the paper than I'm going to do in my presentation today, like contrasting my view with other people's views and responding to objections and doing the things that all of you philosophers know we love to do, but are sometimes seen as puzzling in other parts of the academy. So I'm quite happy to talk about those sorts of contrasts, but I'm going to be focusing mostly on the positive account that I want to give. So the positive account that I want to give is about idealization and how it relates, in my view, to explanation and emergence. Now, the importance of idealization comes about because Galileo kind of initiated a new way of thinking. Well, that's not exactly right. There are other people before Galileo who used idealizations in describing physical experiments and constructing models of physical experiments. But Galileo really popularized them, both in his in different experiments that he used to understand the nature of free fall. Probably Galileo never dropped cannonballs from the Leaning Tower of Pisa. Probably he constructed devices like this to carefully measure and manage the rate of fall of an object in order to come up with his, and similarly with pendula as well, to describe them in terms of a constant rate, their motion in terms of a constant rate of free fall. Now, in doing so, we would say in modern terms that these descriptions, these laws, or these models of the motion of a ball rolling down this ramp or this pendulum when the angle away from the vertical is small, are idealized. They're idealized in several different ways. They neglect air resistance and friction and other imperfections in the system. Now, these idealizations are so mundane within physics. I think Jacob referred to them as the very first things that you may even learn when you take a physics class, right? Is models of phenomena which are explicitly, right, misdescribe certain aspects of them. But there's lots of other examples, not just in introductory contexts, in pedagogical contexts, where this is important. We could name a great number of them. One that is dear to me within modernity is the FLRW metric, or the FLRW space-time. We know that that the contents of the universe are variegated and diverse. The FLRW space-time describes space-time as spatially homogeneous and isotropic. Every place in space is the same as every other, and no matter which direction you look, you will always see the same thing according to that model. And I think it's good for us that that's false. Just look around yourself, right? All of the things that we see are all ways in which the FLRW space-time idealizes. It idealizes away all of the particular details about differences in places and differences in direction. Nonetheless, that model is spectacularly successful. It forms the basis for modern cosmology. There's lots of other examples that one could mention. To take a few very simple examples with which most of us will be familiar, I'm sure. Whenever either in classical physics or in quantum physics, we characterize cross-sections for scattering experiments, we always do so with reference to the flux at infinity, right? We are not calculating, right, what the flux is at some point relatively close to the interaction region. We always idealize it as the flux at infinity. Now, fortunately for our actual scattering experiments, that idealization seems like it's nonetheless very helpful. But in those sorts of circumstances, we're representing something in the world as being something other than it is. We're using a model which is in some way inaccurate. This is the question that is guiding me. What exactly are we doing when we employ idealized models? Maybe to put it a little bit more provocatively, how can something so wrong be so right? Right? How is it possible that we can use models that we know sometimes grossly misrepresent the states of affairs we're interested in to such great effect? These are even perhaps the most extreme when we're looking at idealizations that use infinities. And so it raises the question about whether or not idealizations that use infinities are in some substantive way different from those that don't. The idea being that representing something finite, say, as we often do with something infinite, is the grossest possible distortion that one could make. So these are the guiding questions that I'm starting with my investigation. How do I want to proceed with them? Well, I think that one way of making progress on these questions is by taking some care to identify exactly what we are doing when we are idealizing. So I'd like to give a bit of an account of the form, the function, and the justification for idealizations. I'll try to give some examples familiar to us, but I won't have any particular case study that I'm going to be writing on. After I give that account of what I take the form, the function, and justification of idealization to be, I'm going to address the question that Eli mentioned in his talk about this debate between folks who see idealizations as somehow essential to certain types of scientific activity, particularly explanation, and those who think that it is dispensable. And also, like Eli, I'm going to try to take an irenic middle ground, try to show why the different camps in these debates, they're each right when construed in the right way. And in order to do that, I need to talk about how idealization facilitates explanation when it does, and how I think that the way that it does that is through emergence. Okay. Now, before I get started on what I take the form, function, and justification of idealization to be, I do want to give one caveat to the scope of what I'm trying to do. I take my project to be what I call like gently normative. I'm trying to suggest a classification that I think is going to be helpful. It's not descriptive or empirical in the sense that I don't take that what I'm going to be saying describes the many variegated and probably so variegated that there's no consistent description of how people use the term and understand the concept of idealization. But what I'm hoping is that my explication, for those in philosophy, I'm taking this in the Carnapian sense, helps us order how imperfect models fit within the scientific endeavor. Sometimes folks in philosophy describe this in terms of conceptual engineering. I have a goal, which is to order our understanding and our thought regarding these sorts of practices, particularly as they arise in physics. And I'm hoping that what I'm doing will help with that. Okay. So having covered that point of scope, let me now go to what I take the form, function, and justification of idealization to be. So let's start with the form. So this is the kind of the nutshell statement. Idealization is a model of some phenomena within a certain class of models that is less representationally accurate than another in that class. So as I'm construing it, idealization is actually a four-place relation. First, there's the phenomena to be modeled. I hope you don't mind, I'm going to do a bit of drawing here. So we've got phenomena on the one hand. We also have relations of similarity between instances of that phenomena. What I mean by this is, for instance, phenomena might include field values or positions of various sorts of objects, their momenta, their velocities. Each of these quantities has a structure given to us by the measurement theory for those quantities, which tells us how the different values of the quantities are similar to one another. Oftentimes, it'll be the obvious thing, right? If something is real valued, the relations of similarity will be encoded by the topological structure of the real line. But however it's given, right, this phenomena is not just a space, but it's a space that has structure on it that you might describe by a structure of similarity or even a topological or a uniform structure. We also have a class of models that we take to be representing those phenomena. So in physics, these models are often mathematical in nature. They don't need to be necessarily, though. They could be physical models. I'm just realizing how poor my handwriting is. If at any time I write something and it's unintelligible to you, maybe you can alert Jacob or quickly alert me and I can rewrite it. I'm sorry about that. So the models represent the phenomena. So what that means is that this part here is not just a collection of, say, mathematical objects, but includes a map from models to phenomena that tells us how the models represent. It takes models and maps them to what phenomena that they represent. Now, I'm not making any assumptions here, for instance, that this map is bijective or even that it's surjective, for instance. It may not even not be injective either. There may be phenomena that we're interested in that's not covered by any model. It may be that more than one model covers the same phenomena. These are all possibilities. And then finally, a particular model within that class. That particular model is the idealized model. So I might, just for the sake of visual clarity, describe it by this particular star here. Now, a few things that are important to note here. The relations of similarity amongst the phenomena, once combined with the representations, the representation maps, induce similarity relations on the models. If the similarity relations are given by a topological structure, for instance, this would be the initial topology induced by the representation maps. And what this allows us to do is it allows us to describe how models are similar to one another in virtue of how they represent phenomena. And that allows us to capture what it means for, within a class of models, one model to be more or less representationally accurate than another. We have some phenomena that we would like to describe, and we can describe using the relations of similarity amongst the phenomena along different dimensions, how, for instance, a model, which is mapped over from the space of models to the phenomena, how close it is in various ways to the phenomena that we intend to represent. So whenever there is a model within the space that is more representationally accurate for the phenomena that we are intending to represent, then that initial model we started with, we say, is idealized. One point of clarification I think that's important here is that we needn't be able to explicitly identify what the witness, as it were, to idealization is. The witness is just the more representationally accurate model. And oftentimes in practice, we are not able to do that. We just have some generic information or inductive evidence or a good hunch or good theoretical reasons to suppose that there is such a model. Now, one of the things that this means is that on my account, in order for a model to be idealized, we have to be talking about a specific class of phenomena that we're intending to represent. And as that phenomena, as if we vary that phenomena, whether or not a particular model is idealized may change. Okay. So in addition, I'd like to emphasize that the collection of models is often only tacitly given, often vague, and often elastic. What I mean by elastic is that as new considerations within scientific work are introduced, the class of models considered may shrink, it may expand. As I mentioned, whether a model is idealized according to this is going to depend on our understanding of the phenomena. As we gain more information about phenomena, right, we may come to realize that a model that we thought was not idealized in certain ways actually is idealized in some ways. Models failing to represent phenomena without evidence of idealization can be an impetus to new discovery within science. So in the famous example, for example, of the prediction of the existence of Neptune by Leverrier, we see this example whereby increasingly accurate measurements of the position and trajectory in the heavens of the planet Uranus give us reason to show that there is no empirically adequate model within the Newtonian class of models that were considered that would accurately describe the phenomena unless a further planet was postulated. Good. A little bit more also on representational accuracy. So for every aspect of phenomena that we wish to represent, there's a way to idealize. Maybe I can give you a really simple example. This is a toy example, but I think it really helpfully illustrates the point. Suppose that we're interested in a situation where we want to model a helicopter. Dupe. I guarantee you that this is a helicopter. Now, as you know, helicopters have a main rotor and they have an axial rotor. Now, one of the things you might do when you're modeling a helicopter is modeling both its lift and its rotation around its central vertical axis. Now, one thing that you might do in order to do that, right, is you might represent the lift generated by the main rotor. In doing so, you idealize away the torque that the main rotor generates, the rotational momentum that it generates in the body of the helicopter, and also idealize away the effect of the axial rotor. So we might imagine a model which is only lift, and we might imagine two other models that incorporate one but not the other of these two other features. Here we add in angular momentum. That looks like Tang Mom, which is not what I am intending to convey. Let me rewrite this. Good. Or we can add in, when we de-idealize, represent the helicopter more accurately by introducing the effects of the axial rotor. That's this one right here. Now, if we de-idealize in this way, we add in the effects of the angular momentum of the main axis, our new model will predict that as the helicopter rises, it'll also spin around. In doing so, right, in introducing one aspect in which the helicopter, in making more realistic or more representationally accurate one aspect of the helicopter, we make another aspect less accurate. Because as a matter of fact, I'm postulating when the helicopter rises, it doesn't spin around. And the same thing happens when we look at the effects of the axial rotor only. Including that only in the model, we'll have a model whereby the helicopter will be spinning in the opposite direction as it rises. And then when we combine the two, we finally get a model which is accurate in all of the respects considered so far. So the reason why I'm going through this elementary example is that I wanted to illustrate that accuracy is in general a partial order. There are many dimensions to which a representation can be accurate, and one model can be more accurate than another along some dimension, but not along another dimension. So idealizations distortion, this is often a way that people describe idealization, is a distortion. If you want to describe it as a distortion, that distortion on my account is local, not global. It's away from a better model, not away from the truth. Now, I know that Patricia said a lot about how realists can understand idealization. I'm not opposed to that, but I would like to have my account of idealization be acceptable to empiricists as well as realists, ones in particular who are averse to postulating a one true model that really represents the phenomena perfectly. And one of the advantages that I see of my account, by which idealization's distortion is local, is that it doesn't require in the class of models considered that there be a perfectly representing model. In order for something to be more accurate, in other words, it's not getting closer to the perfect model, it's simply rising up the partial order of accuracy in some way or another. Good. So here's a nice example that also includes some abstraction. We might imagine a situation where the phenomena are the heavens, and the similarity relations between the phenomena are originally trajectories in the night sky. So paths over time on S2, effectively. Initial models of these motions might be given, and over time they might be adapted so that they describe not the phenomena, not just as paths in the night sky, but also trajectories through space and time. So a spatial model of the heavens. In doing so, right, the phenomena itself changes, and the ways in which two models might be similar might also change. So the way abstraction works here, of course, is that after it was discovered that the planets have color and width, nonetheless, the astronomical models didn't need to take into account those objects. Even at the time of coming to the time in the 17th century with Newton, most astronomical models still represented the heavenly bodies as effectively point objects. So one can understand this through a process of idealization and abstraction by which one removes properties from that the phenomena have, but that are not represented at all in the models. So one way that models can be inaccurate is through distortion, but another way that they can be accurate is by omitting properties. Okay, so now that I've talked about the form of idealization as I see it, let me say a little bit about the function. Why use it? Why do it? Now, we've already talked about a bunch of types of examples. Commonly said, and philosophers love this particular answer, to facilitate computation or prediction. That's certainly true, but it's also true that these are not the only reasons. In the last Q&A session, we talked about pedagogy. That's sometimes a good reason to use an idealized model. Another reason that Eli has explored is exploratory usages, so questions in the context of the pursuit of the development of new theories, and that it enables explanation and that it promotes understanding. So there has been a tendency in some of the philosophical literature to correlate specific types or subtypes of idealization with particular functions. And I want to resist that correlation. I think that there is nothing essential about any particular subtype of idealization that ties it essentially to any of these functions. Any of them can work. And the reason why they do is that distortion or omission can aid in these activities. Because if the thing that we want to compute or predict is not sufficiently affected by the distortion in some other element of the model, that helps us in our aim. If our aim is to induce better understanding in our students, distortion in other aspects that is not essential to that understanding can be worthwhile to induce it. In order to make progress on a research program, distorting aspects that we don't at the time consider essential, or only if they become important or only secondary or tertiary to our main research interests, can aid in that activity. And depending on what we want to explain and what we want to understand, distorting aspects not substantially relevant for those explanations or understanding can aid in explanation and understanding. I don't want to understand, and I'm going to come back to this at the end of my talk, I don't want to understand explanation and understanding as a binary thing. There are better and worse explanations, and there's greater and lesser understanding, broader explanations and narrow ones, broader understandings and narrower ones. Sometimes our goal is to have a particular sort of understanding or explanation, and distortions and omissions can aid in those. It's a trade-off. You trade off one kind of goodness for another type of goodness. Trade off one type of, usually in the case of idealization, representational goodness for the goodness in some other sort of scientific activity. That's the function of idealization. Okay, so is this justified? Like, is there a epistemic justification? Like, is this a part and parcel of scientific rationality? The orthodoxy within philosophy of science says that using idealized models is justified when their distortions make little difference to the modeling task within. I actually surprised myself by hewing pretty closely to orthodoxy on this, actually. I think that this is basically right, but I think that we can make this idea a little bit more precise. So first of all, when we say make little difference within the class of considered, that's always with respect to an upper set of the representational accuracy ordering. So if you go back to my little mini Hasa diagram that I drew before, where we have different dimensions of representational accuracy that are represented by the upwards direction in this diagram. When we say that an idealization is justified, what we're referring to is why it's justified in using, say, this model here to represent the phenomena when there are more accurate models. And according to my account, they make a little difference when there is an upper set of the ordering. So some element, which is more representationally accurate, and all of the elements higher in the representational accuracy ordering than it, such that all of those models in that upper set would come to the same conclusions or enable the same sorts of conclusions in the modeling task. The reason why this is a little bit complicated has to do with the sort of example that I just mentioned before, whereby with the helicopter, there are some models which are more representationally accurate in some ways and less representationally accurate in other ways. And we have to be a bit careful just by saying that for all more representationally accurate, for all models that are representationally accurate in some way or another, that it makes little difference. If we're interested in describing, for example, the motion of the helicopter, we do have to be careful about idealizations, particular changes to the model that may interact in the ways that the ones for the helicopter that I mentioned. Now, the other thing that I want to say, which is a complication for the orthodoxy, but I think is an interesting philosophical project, is that establishing this in on good terms is difficult. It's really difficult, actually. In practice, we don't actually show that, in the words of some other philosophers, that de-idealizing always makes little difference to the modeling task. In practice, what we do is we give examples of particular de-idealizations to build inductive evidence that the de-idealization doesn't matter. And some folks describe this as a part of robustness analysis of idealized assumptions. To understand whether a model is robust, we try to modify some of the idealized assumptions to see whether or not we can satisfy this justificational clause. Let me give you an example which is dear to me. So this example is also from FLRW Cosmology. So you might be worried. You might think, how much of our conclusions about the nature and history in the large scale of the universe depend on these idealizing assumptions that everywhere is the same and every direction is the same, right? The homogeneity and isotropy conditions of the FLRW metric. Well, one of the things that one can do is one can show how these idealizations could be relaxed or justified in virtue of other phenomena that we can measure or approximately so. So I have in mind, for example, the Ehlers-Geren-Sachs theorem, which shows that if we have a uniform, under some additional assumptions that I'm not talking about because this is a non-technical talk, but the theorem says that if we have essentially a uniform in all directions cosmic microwave background, this determines the class of cosmological models to be FLRW models. Now, one of the things about that theorem is that it assumes precisely uniform CMB, and that itself is an idealization. So by relaxing that to have almost uniform CMB, one can try to prove theorems to show that the result is at least an almost FLRW spacetime. And some work by Schoger, Mattens, and Ellis have done this. And there's some follow-ups and discussion about how well this succeeds and the limitations of it. But this sort of work is the sort of work that I have in mind as the scientific work that goes into providing us evidence that our idealized models, the use of our idealized models, is justified. Contrary to some philosophers, so I'm thinking here of some recent, very stimulating book by Angela Potocznik, I think that scientists do often try to check or verify or justify their idealizations. Their idealizations are not generically unchecked. Okay. I wanted to say one more thing about the comparison with approximation. Patricia brought this up, and there's a context of a very nice article by John Norton where he draws that distinction. So what, on my view, is the difference between idealization and approximation? I think that approximation is actually quite similar to idealization, but it concerns usually one or at least very few properties of phenomena. In order to understand what an approximation is in contrast, we consider the space of models that kind of gets replaced by a space of values of property. So let me give you an example here. So we can imagine here we've got our phenomena, we've got our models, we have some representation relation between them, and the phenomena is complex. And so in particular, there are going to be particular sub-properties of the phenomenon. They're represented by sub-properties of the model. So we might have a map from the model space into a property space. This might be something like the mass of some important object in the models. And by means of the representation relation between models and phenomena, we can induce how the values of these properties are connected with the parts of the phenomena. And we could talk about category theoretic descriptions of how that's supposed to work. That's not super important. But what is important is that we've got values of a property in a model, and we also have the values of the property within the phenomena. And we can compare these with one another. When we do an approximation, instead of comparing different models and how they represent phenomena, we're only comparing different values of a property and how they represent, as it were, parts or components of a phenomena. So one significant aspect of this is that an approximation may not pick out any particular model in the class of models considered. If we represent one value of a property by another value of a property, there may not be any pre-image of that value within the models. Nonetheless, it's going to play a very similar role to facilitate the same sorts of activities, scientific activities that I mentioned. So the main difference then between idealizations and approximations has to do with, or what you might call idealizations and mere approximations, has to do with whether one is using a full model of the phenomena, or one is only using a part or a component of it. Let me give you a concrete example of this. So my favorite, very simple example is treating Newtonian gravitation as a central force. So one of the first things that we do when we learn about classical Newtonian gravitation is we consider the two-body problem. We imagine a central object, very massive, compared with a lighter object that is in orbit around it. And we calculate various features of the orbit. We prove, right? I don't remember if you all remember this. It was an exciting time all those years ago. You show that it's an ellipse, and you calculate the properties of those ellipses as determined by the properties of the central object and the orbiting satellite. Now, in this treatment, right, oftentimes what one will do is one will describe the force field that is induced in this space, not as one which is exactly described by the interplay between the two objects, as is demanded by Newton's law of gravitation, but as a central force. So instead of saying that the force between the two objects is proportional to the product of their masses and the inverse square of their distances, instead, you only focus on the force on this object, which is going to be just proportional to the inverse square of its distance. In that sort of situation, we approximate the placement and the force field induced by one that is, strictly speaking, not a model of Newtonian gravitation. It's not a model of Newtonian gravitation because, according to Newtonian gravitation, of course, any two massive objects exert forces on each other. And so we don't, strictly speaking, have a central force here. The central force model is not actually a model of Newtonian gravitation. It's an approximation to a model of Newtonian gravitation, because there is no possible state of affairs that Newtonian gravitation describes where there is a precise central force. Okay, so we can see from this sort of example that if you weren't really into classifying like what is an idealization and approximation and distinguishing between them, you would see these as being of the same piece. I think the reason why you would see that is that on my account, they perform all the same sorts of functions. The main difference between them has to do with what aspects of models they represent, entire models or only parts of models. Okay. So now let me come to how I think idealization facilitates explanation and related activities. So this is a little table that summarizes the sort of positions that Eli was talking about in his talk. These terms are also due to him, the essentialists and the dispensabilists. The essentialists think that idealizations are essential for certain types of scientific activities. They think that they're essential for explanation, for instance. And as Patricia talked about, that's often taken as input to an argument that proves problematic for scientific realism. One thing that hasn't been talked about is that essentialists also align themselves with a general idea that emergence is common, important, and useful in science. That the way that idealizations, which are essential, play a role in explanation is that they give rise to emergent phenomena. The dispensabilists, on the other hand, see the sort of role of idealization as pragmatic, not essential, and they are more inclined towards a kind of reductionist program. Now, my own thought is, let's have all four of these. Now, how can I do that? The way that I think that I can do that is by carefully distinguishing different ways in which idealizations are essential or pragmatic, and differentiating particular ways in which emergence and reduction can be compatible with one another. So that's my goal. Okay, let me start with explanation as a prototypical example. I think it would apply probably equally to cases of non-explanatory understanding, although whether or not that's a thing is somewhat controversial. So I'm just going to stick with the explanation case. Now, idealizations, on my account of what idealizations are, if they are justified, not essential to providing explanations full stop of phenomena. But what they do is they often enable better explanations. So Eleanor Knox has suggested that they may do this by facilitating abstraction, facilitating the ability to remove the representations of properties from a model that are inessential to the explanation. So thereby simplifying the model and simplifying the explanation. I think that happens sometimes, but sometimes it's more complicated. Sometimes those better explanations are facilitated by introducing new concepts. And that introduction of new concepts is what I take to be a relevant sort of notion of emergence in science. I am taking here, and I have a more precise account of this that I've articulated elsewhere, that emergence is a sort of comparative novelty. One property in a model is emergent in another, right? Just when it is new and can't be explained why or derived from those other models. And I do take that this sort of comparative novelty is compatible with reduction when we understand the reduction of one model to another, one class of models to another class of models, as a relation of how the one class of models explains, say, the empirical success of another sort of class of models. So a nice example that people often use, and Patricia talked about in quite some detail, have to do with phase transitions and universal properties. A classical definition of phase transitions involves discontinuities, right, in some derivatives of the Helmholtz free energy function. And it's easy to show that this function here for a finite number of summons is going to be a sum of analytic functions. And so itself is always going to be analytic, and in particular is never going to be discontinuous in any of its derivatives. We need to have an infinite number in order for that to happen. And this is why people use the thermodynamic limit, which allows one to have an infinite sum here, and thereby allows one to represent phase transitions as discontinuities in some derivatives of this function. And that facilitates really nice explanations and diagrams where we can draw things like a phase diagram of water, for instance, with a very nice triple point doing something like this. And where the boundaries here are the coexistence curves for the different phases. Now, in these particular cases, we represent the phenomena, which are actual boiling cups of water or so on, with these models, because it facilitates a very clean and simple explanation of the phenomena of boiling that we see. Now, of course, if we had precise enough microscopes and were able to carefully track them, track all the different components of the water, as it boiled, we would be able to see that, of course, the motion and behavior of the water acts smoothly, because it is composed of a finite number of components. And so there's a certain amount, if we were to use a finite model, a certain amount of vagueness or imprecision that would arise in our characterization of these coexistence curves. They would be more like good enough coexistence regions as far as we're able to measure. I think that that's also a good explanation of phase transitions, but in some sense, the one that uses the idealized model is better in certain respects. It's better at articulating, honing in on an essential idea about what is responsible in the model for phase transitions. So even though idealizations are not essential to providing some explanation of how a phenomena arises, it sometimes facilitates better explanations of the phenomena, better according to our human interests, not because it more accurately represents the phenomena, but because it's better attuned to our explanatory interests. Good. So I'm at the last slide, Jacob. So let me come back to my guiding questions and some answers that I'm giving to them. So what exactly are we doing when we employ idealized models? We're using a model not as representationally accurate as some others available. So how can something so wrong be so right? It's because we're trading representational accuracy for some other scientific good. For instance, trading representational accuracy for scientific power or deeper understanding. Now, one of the things that you might have noticed here is that even though I've invoked particular examples where idealizations are infinite, there's no special role for infinite idealizations as opposed to other idealizations. When they're effective, they're always because they give rise to things like emergent properties in the new model that give us this new good in exchange for representational accuracy. So my answer to this last question, are idealizations using infinities substantively different from those that don't? My answer, no. Thank you.
Thanks for the wonderful talk. All right, so I'm going to stop the recording now.